In this video, we're going to talk about how to compute volumes by cylindrical shells. So just to recap, in the previous lesson, we learned the method of disks or washers. And in that case, you would compute the volume using the following setup or formula. The volume was equal to the definite integral from a to b of pi times r squared. Sometimes it's dx, sometimes dy. We looked at several examples. That's for disks. And then for washers, you would have the definite integral from a to b of pi capital R squared, the outer radius, minus pi times lowercase r squared, the inner radius dx. Now, when using disks or washers, the methodology was we were slicing our solid perpendicular to the axis of rotation. Now we're going to learn the method of shells. So we're still going to be computing volumes of solids of revolution, but we're going to look at a different way or approach to compute the volume. And the setup is as follows. The volume is given by the definite integral from a to b of 2 pi r h dx. And when you use the method of cylindrical shells, you peel parallel to the axis of rotation. So that's the main difference. When you're setting up using disks or washers, your slices are taken perpendicular to the axis of rotation, where with shells, you're peeling parallel to the axis of rotation. Okay, so here's the idea. You have your solid, right? You have your area, the region that's first being spun. So here I have bounded. We've looked at this before. We have this region from a to b, our function, and then say we're going to revolve it around the y-axis in this case. And so the following solid results, this is just a hypothetical example, as you can see here. Well, how do we compute the volume of that solid? Well, instead of taking slices perpendicular to the axis of revolution, so instead of taking slices that are stacking in the y direction, instead what we're going to do is peel parallel to the y-axis. So it's almost like you could think of peeling an onion or something like that. You can peel the outer layer first, compute that volume, then peel the next layer off, compute that volume, and then you sum it all up together. And notice here, when you unroll each of these little peels, you're going to get a cylinder. Okay, and obviously the process is we're going to make infinitely many little peels so that we get the exact volume. So when you unroll one of these peels, right, one of these cylindrical shells here, the radius is equal to x. And that might change depending on what you're revolving about, so we'll look at that. But that means the length of the side here of this rectangular section is going to be 2 pi r, right, which would be the radius of the circle to get its circumference, but in this case it's 2 pi x. Then the height is going to be given by the function, so that's f of x. And that's the area, so then if I want the volume, I'd have to multiply that by delta x. So that's basically where our formula comes from for volume using cylindrical shells. The 2 pi x is 2 pi r, whatever the radius is. F of x gives us the height, and then we have dx. So each of these cylindrical shells, when we unroll them, we get a rectangular solid, right? Very thin solid. That delta x is that third dimension. And we're going to sum all of them up. That's why we have our integral, so that we can get the volume of the solid. Okay, so let's look at some examples. And for some problems, you could set them up either using shells or disks and washers, and you can try to compute both ways. Other problems, they're too difficult to integrate with respect to one variable, so you kind of are stuck using a particular method. All right, let's look here. So example 1, find the volume, sketch the region and a typical shell. So we have y equals x squared. So we know what that looks like, parabola. And then it's bounded by y equals 0, so x-axis, and x equals 1, and we're spinning it around the y-axis. Okay, so I'm just going to draw that sliver of the parabola in the first quadrant between 0 and 1. Here's the x-axis, here's the y-axis. We're going to go out to 1 here, and this is 1 here. So here's our parabola. Y equals x squared. It's bounded by x equals 1, y equals 0. So the region that we're going to revolve is right here. Okay, and we're spinning it around the y-axis. Now in this case, I'm going to draw what gets reflected or results from the revolution just in a lighter color. So you know it wasn't part of the original area. And add a little bit of detail so we get a feel for what's going on. Okay, so now we're going to use the method of cylindrical shells, which means if I'm revolving around the y-axis, I'm going to peel parallel to the axis of revolution. So my peels are going to be stacked in the x direction, which means for this problem, I'm going to integrate with respect to x. Okay, now I'm going to draw a typical shell so that we can identify what all the components are for our integral. So say I draw a cylindrical shell right here. Okay. Remember, the formula for the volume is going to be the definite integral from a to b of 2 pi r h, and then we decided we're integrating with respect to x, so dx, which means I need to identify what r and h are. So right here, this segment is r, and you can imagine if I were to draw another shell, maybe over here, r would change, right? But r is given by whatever the x coordinate is, okay? So I'm going to get rid of that second shell so the picture's not so messy, but we can see that r is equal to x. Whatever the x value is here, that's the length of the radius, okay? Now what about the height? What is the height here of this cylindrical shell? Well, the height, you could think of when we found the area between two regions. We have the top function and the bottom function, top minus bottom. Well, what's on top bounding that region, or the height of the cylinder, it's going to be x squared minus 0 is on the bottom. So that's just x squared. So that's our typical shell. Okay, so now we can plug everything in. My limits of integration are going to be from 0 to 1. Okay, students sometimes get confused. They look at what results after they revolve the region, and they want to go maybe from -1 to 1. But remember, the volume is based on spinning that original region, which only existed between 0 and 1 initially. Okay, so base the limits of integration on the region that you spin, not the volume that results. Then you have 2 pi. R is x and h is x squared dx. Okay, and then let's pull that 2 pi out of the integral. Then we have integral from 0 to 1, x cubed dx. So antiderivative is going to be x to the 4th. I'll divide by 4, so I have 2 pi over 4, x to the 4th, evaluated from 0 to 1. That's just going to be 1. So I'm left with pi over 2. Okay. Now, as a good exercise, you can try to set this up using the washer method, and you'd integrate with respect to y. So think about how you would do that. You have to kind of split up some stuff, but I think you guys would enjoy the exercise and make sure that you understand the difference between the two methods. Okay, moving on, example 2. We're taking this portion of x equals 4y squared minus y cubed. So bounded by that curve, x equals 0, the y-axis, and we're spinning it about the x-axis. So we are spinning it this way, okay? Now let's think about this. We're spinning about the x-axis, so what is this thing gonna look like after we spin it? A little strange, right? Just kind of mirror it over to the other side. Okay, it's gonna be a solid that almost looks like part of a hilly region. And then I'm gonna peel parallel to the axis of revolution, which means I'm going to integrate this time with respect to y, right? Those cylindrical shells are going to be stacked in the y direction. Another big hint that that's how you're gonna have to do it is look at this. X is defined in terms of y, and it would be rather tricky to solve for y. Okay, so here we go. Let's draw a typical cylindrical shell. So I'll just draw one maybe right here. Okay, and then we have to figure out what the radius is and what the height is. So this portion here is the radius. Notice it's whatever the y coordinate is. And then what about the height? What is this height determined by? Well, it's determined by the curve. And I don't have to subtract anything. As the curve changes, naturally the height will change. So if you were to peel somewhere else, like this, right, it'll take care of that. So we're not subtracting anything out. The curve will naturally take care of the shells. So the height is equal to 4y squared minus y cubed. Okay, so it looks like we're ready to go. Let's set up our integral for the volume. The volume is going to be definite integral. Now, what are my limits? Be super, super careful. Only look at the limits for y on the original region. So it's going to be from 0 to 4, 2 pi. Now, what was r? R was y. And then h was 4y squared minus y cubed dy. All right, now let's anti-differentiate. So we have 2 pi, 0 to 4. This is going to give me 4y cubed minus y to the 4th dy. And then I'll leave the 2 pi out here. Antiderivative of 4y cubed is y to the 4th. Then I'm going to have minus 1/5 y to the 5th from 0 to 4. So this is going to be 2 pi times 4 to the 4th, that's 256, minus 4 to the 5th, that's 256 times another 4, so 1024 over 5. If I plug in 0, I get 0. And then I'm left with 512 pi over 5. All right. Good. Now, let's look at another example, and we're going to have to determine what method is best. Okay? So, find the volume by any method. Here we have the parabola, y equals negative x squared plus 6x minus 8. It's bounded by y equals 0, so the x-axis, and we're spinning it about the x-axis as well. Okay, well, to draw a nice graph of the parabola, let's figure out where the vertex and x-intercepts are. So the vertex is going to be at negative 6 over 2 times negative 1, which is 3. And then f of 3 is going to be negative 9 plus 18 minus 8, which is 1. So I know the vertex is at 3, 1. And then the x-intercepts, if you just look at the equation, you can tell it's going to factor, right? Multiply it by negative 1 in your head, and then factor it. So I can tell the intercepts are going to be at 4, 0 and 2, 0. Also, your vertex is always evenly spaced between your x-intercepts. Okay, so let's draw this region. So here's the y-axis. I don't have to go very high, right? Just to 1. And then the x-axis, I'll sketch it out to 4. So we have 1, 2, 3, 4. And then I'll say this is 1. So 3, 1 is where the vertex is. 2, 0, and 4, 0 are the x-intercepts. And I'm bounding this region with y equals 0, which is the x-axis. So this is what we're spinning. Okay. Oh no. So let's think here. If we're spinning around the x-axis and we wanted to use cylindrical shells, okay, since we've been doing that for a while. Okay, well, let's see, what would it look like? So it's gonna spin around this way. It looks like a weird shaped egg, right? And then if I were to set up cylindrical shells, let's think about what we would have to do. So if we did shells, we would have to integrate with respect to what variable? Well, think about it. If you're spinning around the x-axis and you peel parallel to the x-axis, those peels would be taken in the y direction. So we would have to integrate with respect to y. So we would have to solve for x in the equation y equals negative x squared plus 6x minus 8, which is a little tricky. So it would be easier to use discs. Another reason why you wouldn't want to use cylindrical shells is if you drew a typical shell. Maybe you're convinced as is, huh? If you drew a typical shell, so here's the radius, right? The radius doesn't look too difficult. Radius is y. But what about the height? Well, notice the height is composed of two different parts of the parabola. This right piece minus the left piece. So the height is the right side of the parabola minus the left side of the parabola. And as I mentioned earlier, you would have to solve for x, and you'd have a positive and a negative rad, and that's how you would set it up. So that looks like a big mess. Since they're letting us choose what method we want to use, let's use discs. Okay? So what I'm going to do, let's copy this graph over so we can set it up using discs. Okay? Let's get rid of all this shell business. We're not doing it that way. And so on the problems where you get to choose, you have to decide. I usually look at would I rather integrate with respect to x or y and base my decision off of that. Or sometimes it's just easier to set it up based on the way the function's written. Okay? Good. All right, so I'm going to color this back in now and draw a typical disc. So we take this portion, we're spinning it, we have this solid. So what does a typical disc look like? Well, that's going to be perpendicular to the axis of rotation. So these are going to be stacked in the x direction. Maybe you already feel better as I'm drawing this. Right? And then I just need to determine the radius because we do pi r squared. Well, the radius is given by the parabola, which is negative x squared plus 6x minus 8. So that's not too bad at all. Okay, so let's set it up then. So the volume is going to be given by the definite integral. The limits are going to be from 2 to 4. It has to be in terms of x. And then I have pi times the radius, which is negative x squared plus 6x minus 8 squared dx. Okay. And I'll let you work that out. The rest is just pretty straightforward. Okay. One more example. Find the volume by any method. This time we have y equals x, so we know the line y equals x makes a 45-degree angle with the positive x-axis. Y equals 0, x equals 2. So it's a triangle, right? We're bounding that line with the, the x-axis and a vertical line. And then we're spinning it around, oh my goodness, x equals negative 4. So we're going to have a big gap in the middle. So I'm going to go all the way to negative 10. On the x-axis and up to a little bit past positive 2. Okay? So here's x-axis, y-axis, 1, 2, and then 1, 2, 3, 4. That's what we're spinning around. 1, 2, 3, 4. And then here's negative 10. And then in the y direction, I'll just go up to 2. So y equals x, that's going to go through 0, 0, 2, 2. And then I'm bounding it with x equals 2 and the x-axis, y equals 0. So I'm taking this little sweet triangle and we're going to spin it around x equals -4. Spinning it around here. Okay, so what's it going to look like? You see there's this gap of 4 units, so there's going to be another gap of 4 units here. And then you're going to have basically the mirror image resulting on the other side. Something like this. And then obviously this is going to be a weird looking sort of solid. Let's draw the top portion. Okay. Good. Almost looks like the seats of a sporting arena, right? With the middle open. Okay. So you could set up whichever way you want, but let's see if the shell method would work so we can get some more practice and observe the fact that it's a pretty nice setup in this case. So if I were to peel parallel to the axis of revolution, I would have to integrate with respect to x, right? Those peels would happen in the x direction. And here's a typical cylindrical shell. Doesn't look too bad. Okay, now what's the radius for this shell? Well, this little portion here is x, but notice I have to add 4 to that. So the radius is, if you want to think back in terms of when we found areas between curves, it's right minus left. So x minus -4, which gives us x plus 4. Or if just looking at the picture that you drew, you can tell, oh, I need to add 4 to whatever x is to get the radius because there's that big gap in the middle, then do that. And then what about the height? Well, the height is given by the line y equals x, so the height is equal to x. All right, looks good. So let's set this one up. See, that was nice and painless. So the volume equals the integral from 0 to 2. Remember, those limits are based on the original region, times 2 pi r, which is x plus 4, times h dx. Okay, so take the 2 pi out. Then we have the integral from 0 to 2. This is x squared plus 4x dx. So this is 2 pi, antiderivative is going to be 1/3 x cubed plus 2x squared, evaluated from 0 to 2. Then we have 2 pi times 8/3 plus 8 minus 0 if I plug in the lower limit. So this is going to be 2 pi times, so 8/3 plus 8, 8 is 24/3, so that's going to give me 32/3, which is 64 pi over 3. All right, nice work. So which method do you prefer? I've heard both opinions. So hope you enjoyed the video. Be sure to comment, like, and subscribe, and let me know what sort of videos you'd like to see next.